lot of you may recognize this as there have been some lovely pictures of, beautiful scenery. We're the city amongst all of this. And so what I thought to do today is to kind of cover some of the green infrastructure that we've been putting in place since 2010. This initial picture right here, of course, you can see this is one of our green roofs right here. We were talking a little bit about the Mill River. Well, Tan Brook comes from AMHERST. It daylights over here at the Fine Arts Center a little bit, where it goes into our campus pond. It then goes underground again, daylights out just before the Mill River. I know Jason's been great to work with because we are getting some phosphorus loading with the pond. I'm not sure it's geese. I'm not sure it's just sediments over time. So all things that we're working on. But to get back to what I want to talk about, which is more of the green infrastructure. So as probably most of you know, green infrastructure, really, it's about an approach to stormwater management, and we want to protect, restore, mimic the natural water cycle. We want to try to keep that water filtering through where it was meant to be filtered. And some of the things that we look for in our projects, we want to protect and restore native soils and vegetation. We want to try to minimize impervious surfaces, and we want to design our stormwater systems in smaller sections instead of as what the former traditional infrastructure way is. You've got, you collect your rainwater and you just quickly convey it off the property via a catch basin or a storm drain to a receiving water. It does a great job to prevent flooding, but there's issues that are affiliated with it. With high amounts of water, you could get erosion, sedimentation. You get temperature changes. So say we've got a big gigantic parking lot, it heats up in the summertime, and then that sheets off in a rainstorm, and it can cause temperature issues as well as, if there's oils, things like that. You get toxins that can completely just go right into your brooks and ponds. So what I want to start with, since my initial picture showed the green roof, I did not take that picture, but it was very, very pretty, as you'll soon find out. My photography compared to those that are very good at it. But for those of you that haven't seen green roofs before, this was my first project of ever seeing a green roof, and it's way more involved than I ever thought. You need to think about excess water on your green roof. So like this year, we've had several storms of 5 inches of rain. So that's a lot of water that's coming onto that roof. And so you want to be able to think about how you're going to be getting that water off. You also want to think about last year. So you're not getting any rain. So now we want to make sure that we have some sort of way to irrigate our plants that are up on the roof. With all that rain, we need to think structurally. That's an awful between the water and the soils and everything else. That's a lot of weight on that roof. So we want to think about structural issues. And one of the biggest ones is you want to think about waterproof membranes with leak sensors. And thank God that we had these, because as we were constructing this, we actually did have a leak that we couldn't figure out where it came from. And fortunately, when it was just the roof membrane that was on there, we actually had to replace it because we could never figure out. So again, that was kind of scary. And then we also want to think about maintenance. And so this is during construction, and this is after construction. Like I said, not nearly as pretty, but it works for me. So you can see that we've installed a parapet around, because that's a pretty nasty fall if you've got to get up there. And there is maintenance. You need to weed, you need to replace or seed plants, you need to, again, just, you may need to water. So again, it's really important that you have areas that you can walk on without creating and tamping down those special soils that we use on there. And we, in this particular roof, use sedum. The surface area that is green roof is about 15,000 square feet. The nice part is the green roof provides an educational opportunity. It reduces heat island effect. It's a pleasing view, especially for one of our most beautiful sites on campus. It absorbs CO2. It reduces glare. If you look at the white, which is, again, because you don't want a black roof anymore, but you've got the white, which is a lot of glare, and you've got the nice aesthetics of the sedum. And this particular roof will contain about 1,825 cubic feet of stormwater. Additionally, the plant life should hopefully also protect the roof itself because it's not being bombarded by UV light. So hopefully we'll get some extended life expectancy as well. Also look over here. Like I said, there's a Tambrook grows underground here. So we needed to collect a lot of the water coming through here as well, because it's getting in, any runoff would be going right into Tambrook. So we have rain gardens that are developed over here. So let's talk about some bioswale design. So some people think, oh, a bioswale, it's like, oh, it's a place or a rain garden. It's like, okay, we're going to have cattails and it's a wetland. No, most of the time it's really dry. But what you want to do is be able to treat that bioswale during a rainfall. So you've got your top layer, which you want it to be closely packed vegetation. You want a high amount of surface area for contact with stormwater. And the thicker and the heavier the grass is, the better the swale can filter out those pollutants. Again, it's specially chosen plants. Again, we prefer the native plants, but something that's got a high nutrient uptake ability. The next layer that you've got in here is you've got a bioretention soil mix. You want that water to soak in rapidly to treat the runoff, and it's got to support that healthy growth. But underneath all of that is you've got a bioretention or an aggregate gravel. When it goes through the soils, it collects. If the surrounding soils can't absorb it, you do have some runoff through here. So it's now cleaner water because it's gone through a filtering system to your gray water system. Or like this year, if we have a ton of rain, we don't want to overflow our swales. So again, the whole idea about this is to prevent flooding. And so how can we prevent flooding, but still have a lot of that natural water cycle going back into our surrounding soils? Again, small areas versus the big gigantic runoffs. So some examples of this is the John Olver Design Building. This was finished in 2017. And this is the front of the building. You can see it's a fairly steep incline right here. So when we talk about a bioswale, we're thinking about treating it more on a horizontal surface, where a biocell is more on the same contour, and you want to have it infiltrate more vertically. So here we've got a swale on both sides. And I am going to show you, here we go. This is again during construction. And so here is, your bigger aggregate so that your water can run with some check dams or weirs in order to create some ponds. You don't want to carry your soils away. You don't want to carry your plant life away. So this was during construction, and this was just taken a couple of weeks ago. So we've got some good plants that are growing in our swales. Another picture of the plant life, some more water coming through. Again, we've got a nice, healthy ecosystem going on here after 4 years. The next area that I want to talk about is our Southwest Concourse. And this has a lot of green technology that's part of it. It's about a 5-acre piece of concourse that was under construction. The concourse was actually bigger. It's really the central core. But the cool numbers on this one is that prior there was 70% impervious impervious pavement. It's now reduced to 40% hardscape. Originally we had 30% original plantings. Now we're up to 60% for new and restored planting in pervious areas. We actually removed 25 catch basins and several hundred feet of subsurface stormwater piping. And I'm going to take this and break it down, and I decided not to show you the before picture. These are not me, these are compliments of Stimson, who took the pictures after construction. This is a night picture, as you can see. It's impervious, they're porous pavers. And just in case you get lots of rain, you do still have some drainage systems amongst the porous pavers. It then runs out over into here, which are, I learned a new word through this project because I thought they were bioswales, but they're actually called runnels. And these are some metal kind of guide structures instead of a swale type structure. You can see lots of, you've got some of the bioretention soils in here for our plants. And then it's dressed up with, as part of the project, for aesthetically, we took some of our granite pavers as part of this. It goes into different areas for some more biocells. This is a beautiful sitting area. It's all made over wood. You've got some vegetated bios, here. You've got some bioswales along the edge. You've got some kind of rain gardens or biocells in here. You got some tree box filters. Again, they did a really, really nice job on this particular site, and it looks so much better than what it did 11 years ago. The next one I want to show you is our life science labs. This happens to be a rain garden. I think this actually drains from here, goes across the street into the pond as well. So it's nice to see that any runoff that's coming through here is going through some rain gardens as well. We also, from the roof of the life science building, we have a water harvesting system for the life science building as well. And then the last thing that I want to talk about, which was my first project, and I think the first project on campus. Unfortunately, it no longer exists because it was taking runoff from the parking lot where the John Olver building is, which I showed you earlier. And this was a cool project because it was a joint project between Mike Davidson, who is one of our professors here, for landscape architect, in conjunction with our physical plant landscaping and physical plant in general to help with some of the building. And we took, it's about 150 feet long, 20 feet wide, 18-inch deep, and it was handling about 3,000 to 4,000 gallons of water, or could handle that much water. And again, you can see the weirs that were built up so it wouldn't pull the runoff away. So again, I just really like that as a shout out because it was our first project, and we've really been trying to, in our projects, to look at a lot of the green infrastructure to try to put a lot of that water back into our soils instead of having it completely run off into a lot of our gray water systems, especially because they are already overloaded. We've been around since the 1800s as well. And so that infrastructure with the building and everything else, if we just took impervious and surfaces and just ran it down, I don't think we would have the capacity in our drains itself. So just some quick lessons learned. It's really important of accurate site data, including your soils and slopes. You need to provide management of flow during project development and with project completion as well. Having the right plants is important because again, you need them to grow in dry situations, wet situations, and still be able to filter pollutants. We again are trying to do native plants. And here's a big one. You really want to avoid compaction of soils during and after construction. So during construction, you want to be very thoughtful on your swales need to be the last area that are being completed. You don't want your heavy equipment driving over it, because you're going to compact that soil and that water is not going to infiltrate. As well as your swales, they're not going to survive on its own. It's like any garden. It needs maintenance and it needs care. So you want to think about and have your preventive maintenance in there, your pruning, your weeding, you're taking out of trash and things like that. So on that note, trying to get through that fairly quickly. Any questions for me?
Not a question, but a
Okay, now
comment.
I can hear you. I'm like, uh-oh, now I can't hear anybody.
Okay, sorry. I've been just a comment. I went to UMass in the 1980s, and there is just a vast improvement aesthetically and functionally and in terms of sustainability from those days. And I appreciate all the work you and other people have done in that direction.
Well, it's nice to hear that. And like I said, our physical plant are amazing. Our landscapers, they're very conscientious about what they do now, and they're offering up just as many ideas as when we're going through projects. And I also, like for this group, UMass is new to the MS4s, which, do people know what the MS4s are with a nod of the head? But anyway, we encourage public participation when we've started. Of course, COVID has been nasty for us. And so we really haven't invited public in. Hopefully this year will be better.
Go ahead and let them know, Theresa. So the MS4 permits are the stormwater permits that are given to the state, to municipalities, but because UMass is so large, it's sort of got its own special status and has its own stormwater permit.
And it is. So we have, like, our central heating plant has its own NIPDES permit, which is a permit to discharge. So now we're looking at the university like a town. And so we're looking at it, holistically from a number of areas. And again, I don't want to take up too much time. I could actually do this as another presentation, but again, we're looking at it from construction. We're looking at it post-construction. What can we do in order to reduce that phosphorus level or reduce the loading? Like I said, it's kind of weird. Jason has given me some great numbers on the pond, and it's like, what the heck is going on the phosphorus loading? Because we don't use fertilizers next to the pond anymore that would add phosphorus to it. So what's going on? And so I'm hoping that I can continue to use your data, and maybe you can help us out in some more sampling and whatnot to try to figure some of this out.
Well, I think Janice Weldon, who's been working with Nick Tooker on Tanbrook as a graduate student, is going to come up with some very interesting data, both because she's been sampling often, weekly, I believe, in 5 locations up and down Tanbrook, above and below Campus Pond. And also we had just a phenomenal wet year. And so as far as, if you're looking for relational, causal relational issues, this was a great year for collecting data.
Absolutely. And we discovered some other things along the way that we put in, what was it? There's a vortex meter now, or a vortex structure now in the Fine Arts Center to collect things off of Tanbrook. And so a lot of that, because it was, there was a bunch of debris in that area. Yeah. We've cleaned that out. A lot of it was just getting diverted to the soccer fields. Mm-hmm. And so the water was pretty much stagnant in the pond, which I'm sure wasn't good. And I can get you those dates if you need it. but we're still pulling a lot. We empty that vortex structure quarterly, and we're pulling out a lot of sediments out of there. So I'll be curious to see now that we've established a cleaning regimen, which is really started, I think, in 2019. So I'm really curious to see what that data is going to help. We put in some to try to repel a bunch of the geese. If you don't know, geese have 2.2 pounds of poop per bird per day. So with hundreds and hundreds of geese that we're putting on there, and hopefully the fountains, I would love to see looking at some more native plants to try to repel some of the geese from actually entering onto the pond, as well as if there's anything we can do from that standpoint. So again, I really appreciate all people's help and input for what's going on with at least what we can do.
It's been great having you as a partner, Theresa, and I think that collaborative working group with the other engineering elements and facilities maintenance and all that from UMass has been really a good collaboration.